We are now going to consider one more method to improve our estimate of the solution to the differential equation. That method is the fourth order Runge-Kutta method. And you might have guessed that instead of considering the average of 2 slopes, why not consider the average of 4 slopes? So in this case, we're going to average a first slope. So that's f of t0, y0. So we're going to do the slope at the beginning of the time interval. And then instead of moving forward a full delta t, let's move forward half a delta t to t0 plus delta t over 2. And then we're going to consider our estimate half a delta t forward based on the previous slope. So we'll consider it based on y0 plus s1 times delta t over 2. Okay, so again, that is our estimated solution half a time step forward based on the first slope. Now we can consider a third slope, which is again a half a time step forward, but instead of being a half a time step forward from the first slope, we'll do a half time step forward from the second slope. So y0 plus s2 times delta t over 2. And then finally, for the fourth slope, let's go a full time step forward. But again, instead of using the first or second slope, we're going to go forward a full time step in our solution using the third slope, the one that we just calculated, for a full delta t. Okay, and so then we want to average these slopes. So we're going to do y0 plus, and we're going to average the 4 slopes. So we could do s1 plus s2 plus s3 plus s4. And we could average those and divide by 4 and multiply by delta t. But it turns out that a better estimate is actually to use a weighted average. So we could do 1 S1 and then 2 S2s, 2 S3s, and 1 S4. And so since we're weighting those slopes, we're going to divide the whole thing by 6 and use that weighted average. Now, I'm not going to derive exactly why this method works and why we want to use 2 of the middle 2 slopes each. That's for another type of class, a class in numerical analysis. But I can tell you that a lot of these methods come out of understanding Taylor series and using Taylor series to approximate functions. So what you can see from this graph below is essentially how we're getting at the solution, or an approximation of the solution to the differential equation by averaging 4 slopes. Now, this is called a fourth order Runge-Kutta method because the error is actually proportional to delta t to the 4th power. What that means is that if we decrease delta t by a factor of 2, so if we divide that by 2, then our error will get divided by a factor of 2 to the 4th, or 16. And so this is going to converge to the actual solution much faster than either Euler's method or the second order Runge-Kutta method. So I want to leave you with one more picture, and that is a picture of the fourth order Runge-Kutta method. And so what we're going to do is again, we're going to do those 5 time steps. Okay, so we're going to look at the first one, which is the average. You can see it's the average of 4 slopes. So that green negative slope that you see there is the average of 4 different slopes. at the beginning of the time step. 2 of them are halfway through the time step, and that 4th one is at the end of the time step. Okay, and so we're going to build our solution like that, each time using 4 different slopes. Okay, so we're going to build it here, and hopefully you can see that again, this does not drop as dramatically as it did with Euler's method, and that gives us a pretty good approximation. In fact, if you roll back to the previous video, this approximation is pretty close to the one that we got with the second order Runge-Kutta method. What I'd like you to see though is that when we were using Euler's method, okay, so we had that big dramatic drop there, right? And our estimate of y was 3.75, and the error for that estimate, because we can't actually solve this one exactly, was 0.2448. We moved to second order Runge-Kutta and then improved our estimate to 3.9876, right? And the error was now 0.2022. So we improved in the error category. Before it was 0.24, and then now it's 0.20. If we move to the fourth order Runge-Kutta, I want you to notice a dramatic increase here, or in the accuracy, because now my approximation of the solution is 3.8676, but my error is only 0.0055. Okay, so if I look at all 3 of them compared, you can see that the blue one, which is Euler, dramatically drops at the beginning. The Runge-Kutta second order doesn't drop as much. And then the fourth order Runge-Kutta, it starts to drop kind of the right amount, and then it carries back through, and it gives us a better estimate of the solution to the differential equation. So remember that the fourth order Runge-Kutta, this is kind of nice to know, gave us an error of 0.0055. That was an estimate of 3.8676. What's kind of fun is we go back to Euler's method. Maybe we use 100 time steps, okay? And we solve, okay? So that looks nice and smooth there. We're going to move down to the bottom of the error. And notice with 100 time steps, we got an estimate of 3.8554, and then the error was 0.0093, and that looks like about almost double the error of the fourth order Runge-Kutta method with only 5 time steps. So the fourth order Runge-Kutta method is much more efficient.